So hello everyone, my name is Nikos, and today with Kay we're going to be presenting our latest work called Localizing Task Information for Improved Model Merging and Compression. And this is a joint work with Guillermo Ortiz Jimenez, François Fleuret, and Pascal Fossat, and was recently presented at ICML. So just to give you a bit of context, in the last few years, there has been a paradigm shift going from training our models end-to-end to actually taking advantage of all the pre-trained checkpoints, all the foundation models, because they have superior performance, they have many other benefits. But because of their sheer scale and computational requirements, there has been a lot of work on trying to make them more efficient. And this has many different facets. So it can be a mixture of experts, parameter efficient fine-tuning with LoRa, ADA LoRa, and so on, quantization and model editing, which focus on training, fine-tuning, serving, inference, and all these different things. And in the meantime, there has been work on trying to understand the optimization landscape or the loss landscape. So, for example, it was shown that if you have two different solutions which are you derive from different initializations, you can actually connect them with a path of low loss, which is non-linear. And if you extend this to, if you share some part of the optimization trajectory, this can also be a linear path of low loss. And going one step further, you can say that all these different local minima that exist from different initializations are essentially the same modulo permutations, roughly speaking. And understanding this, having all these insights on the optimization landscape has allowed to derive many different algorithms that try to bring the benefits of ensembles to the modern deep learning era. So all the different ensemble techniques that exist in terms of a prediction ensembling, having many different models, we try to bring them over to deep learning models, but we don't want to have n different models because this scales linearly the inference cost and the memory cost. So we want to combine everything into one model. And this brings us into all these ideas of weight interpolation and weight ensembles. And some of them are like stochastic weight averaging, robust fine-tuning, and model soups. So given all this and the fact that there are really a lot of different fine-tuned checkpoints on Hugging Face or on different platforms, which are mostly derived from the same few foundation models, a question that naturally arises is, how do we leverage all these fine-tuned checkpoints to construct multitask models? Because most of these checkpoints are usually just for one task. And if we want to extend this to multitask models, one naive solution is to take all the tasks that we care about, for example, MNIST and CIFAR in a very simple example, and then fine-tune on the union of these datasets. But as the number of tasks increases, the potential combinations grow exponentially. So this is not a very elegant solution. And what we want to do is take advantage of all these ideas and insights on the geometry of the loss landscape and bring them over to construct multitask models. And a very elegant solution was proposed by Larco et al. In editing models with task arithmetic, the original paper, where what they essentially show is that starting off from a pre-trained checkpoint theta 0, you fine-tune and you get theta, which is your final checkpoint. And the difference between the two is called the task vector. And essentially what they showed is that the arithmetic operations between the fine-tuned weights usually produce analogous functional behaviors. So if we have only one task vector, for example, we can fine-tune on a behavior that we don't want our model, for example, toxic comments, and then instead of adding it, we subtract it, and then our new model does not have this undesired behavior. And actually, what we're going to focus on this talk is learning via addition. So going back to our example of MNIST and CIFAR, instead of fine-tuning on the union of the datasets, we simply fine-tune on each of the datasets independently, and then we add the task vectors up, and magically the model has become multitask. So on a very high level, we start from theta 0, which is the pre-trained checkpoint. We fine-tune on different tasks, in this case 3, and we take the differences and we collect them. We collect all these task vectors. And then we define a merging function f, which takes all these task vectors and produces the multitask vector. And in its simplest case, it can be simply adding all these task vectors with some coefficients. And then our final model is this multitask vector multiplied by a scalar which is tuned on a held out validation set, plus the pre-trained weights. And this is our multitask model. And this works, especially when the number of tasks is small. In terms of works, I mean that the performance of the model, of the individual models is kept. However, if we keep adding more and more tasks, this is not the case. And there are significant performance losses. So for example, on the standard VITB32 experiment from the original checkpoint, from the original paper, which has 8 tasks, we see here on this table from ties merging that even though the original 8 checkpoints give us an average performance of 90.5, if we do all this merging, which can be task arithmetic or the proposed algorithm ties merging, you do have some significant loss in performance, and this might not make the model usable because of this huge difference. So in the original ties merging paper, they proposed one issue with this, one issue that brings on this performance loss, which is weight interference. The fact that on a single parameter, you have 8 different versions from 8 different tasks. And when you try to merge into one, you might have conflicting signs, and maybe the important parameters are compromised, and this leads to this performance loss. In our paper, we propose 2 different hypotheses. One of them is information erasure, the idea that the task-specific information on each task is erased when you actually construct the multitask vector. And the other one is task interference, the fact that the important information is actually preserved in the multitask vector, but due to the interference between the tasks, it cannot manifest properly. So in order to test these 2 hypotheses, we do a controlled experiment. So here we depict the weights of a model, and during the standard fine-tuning, you can actually use all these different weights and to construct the task vector. In this control experiment, what we do is that for the 8 tasks, we divide the model into 8 different subsets of weights, and then we fine-tune each task on its different subset. And then we try to see the effect of this change. So in the standard fine-tuning, when you have access to the full model, you get something like 92.8 average performance on the 8 tasks. And if you do the same fine-tuning with your controlled, with this control fine-tuning, you get a bit less because the expressivity of the model is not as high as in standard fine-tuning. And now going on to task arithmetic, we saw from the previous table of ties merging that you do have significant loss in performance. So in terms of going from 92.8, you go to 71.5. And you would expect that maybe because we don't have these conflicts between the parameters in this very specific setting, that in the controlled experiment, we will not have such an important drop. However, we do have the same kind of drop, the same level of performance drop, as we can see in the normalized accuracy. However, there is a big difference here. Since we have predefined the weights that each task is fine-tuned on, we can use this as a mask to mask out all the different weights that come from the other tasks. And if we use this predefined mask on this on the new multitask vector, then we can get 100% normalized accuracy because we fall back to our original model. However, if we do this, we're kind of dependent on this control fine-tuning, which is not used, and all the different checkpoints that exist out there do not use something like this. So a question that naturally arises here is that, is this actually happening naturally? So is this information that actually exists in the very specific way that we have created the multitask vector, does this actually happen naturally? So what we have essentially is individual task vectors. And here the opacity of the color means how large the norm is. And having 4 tasks, we try to merge them into a multitask vector. And this merging can be done with any of the existing methods that can be task arithmetic or ties. And then we want to, instead of having this mask predefined, we're trying to actually construct this and pinpoint the important information for each specific task. So the mask construction algorithm takes into account the multitask vector and the single task vector for a specific task, and we try to construct a mask that essentially localizes the important information. And this is done essentially to approximate the original model through the multitask vector. So overall, the idea of the algorithm is to approximate the original task vector through the multitask vector with a sparse binary mask. And at this point, I will give the talk to Ken.
Thanks, Nikos. So I'll pick up from here. So right now the aim is to find the sparse binary mask for each task, which allows us to approximate original theta t as we have seen here. So the next question is, how do we construct this sparse binary mask to extract only the relevant parameters or the relevant information from the multitask vector? So a reminder that the ultimate goal is to reconstruct the theta t, which is kind of approximates the original theta t, which is the fine-tuned checkpoints. And we do that by minimizing the L1 distance between the reconstructed theta t, which is theta t hat here, and the original theta t. And this is equivalent to filtering on the multitask vector, such that we have a filtered multitask vector, which has a very small L1 distance to the original task vector on that task, tau t here. And after a simple derivation step, we arrive at comparing for each parameter the magnitude of this original task vector, tau t, and also the magnitude of the difference between the multitask vector, tau t, tau mtl, and the original task vector, tau t. So, and furthermore, we found that if we add one more hyperparameter on the right-hand side of this equation, we actually improve the performance of this overall algorithm. So we refer the audience to check the paper for more detailed derivation about this part. So in summary here, what we did here is that the first step is to merge the individual task vectors using any model merging algorithm. It could be task arithmetic, which is simply a summation over the individual task vectors, or task merging, which is more state of the art. And we construct the binary masks for each task using our TOMASK algorithm. These binary masks allows us to extract only the relevant parts for each task based on the multitask vector. So we have introduced how we construct the binary masks. Next slide, we will talk about the performance after constructing this binary mask and also filtering the parameters. But before that, we first introduce the performance of the baseline method task arithmetic here. So here we evaluate on a 8-task computer vision benchmark, where we have 8 different image classification tasks. On the x-axis, we have the individual tasks, and on the y-axis, on the right-hand side, we have the normalized performance of task arithmetic, respectively, on these different tasks. So here, the normalized accuracy is the accuracy of task arithmetic normalized by the accuracy achieved by the single task models after fine-tuning on that specific task, which means the best you can do is 100%, and that's the case where we have preserved all the performance of the single models. So as we can see here, the performance of task arithmetic is around like 65 to 75%, which means that there's a large proportion of the performance of the single task models being lost after the model merging process. However, in the next slide, we are going to show the performance of after applying our TOMASK algorithm to filter out the relevant weights for each task. So a reminder that we have a constructed MT for each task, which is the binary mask. We apply this MT to filter out the relevant parameters, all of this tau MTL, which is the multitask vector. We filter out the relevant weights, we add them back to the pre-trained weight to reconstruct this theta t hat, which we aim to approximate the original theta t, which is the fine-tuned checkpoint. And as we can see from this plot, after we reconstruct this theta t hat, we evaluate their performance on the individual tasks. In most of the cases, the performance is around 100%, as shown in this dark blue curve, which means that by applying our Tomask algorithm, filtering out only the relevant weights, we are able to preserve almost 100% of the accuracy compared to the single task models. And apart from that, we have also in this figure the green bar plots, which represent the proportion of the parameters extracted by our Tomask algorithm for each task. As we can see, in most of the cases, actually in all the cases, our Tomask algorithm extracts less than 50% of the parameters from the multitask vector, which is enough for us to retrieve almost 100% of the performance achieved by the single task models. And on the other hand, we can also understand this as the over 50% of the parameters are actually redundant or even harmful for that task. Their existence not only damages the performance on that task, they actually creates task interference for that task and leads to a performance degradation, as we see by the performance of task arithmetic here. So we have introduced the performance of Tomask. In the next slide, we will talk about the application of Tomask. Here, the first application we're going to talk about is model compression. So what we have already known from previous slides is that Tomask allows us to retrieve the performance of the single task models. This suggests that during evaluation, we do not have to save the individual fine-tuned checkpoints or the individual task vectors. Instead, we only have to save a pre-trained model, theta 0, a multitask vector, which can be aggregated using a model merging algorithm, and also the binary mask for each task. As a result, we are not saving floats anymore for the different tasks. We are saving binaries, which is much less costly in terms of storage cost. In this slide, we are going to present the performance of our proposed model compression scheme using our Tomask algorithm. So here in the x-axis, we have an increasing number of tasks, which goes from 1 task to 20 tasks eventually. And we also have on the y-axis, in the left is the normalized accuracy of each method. And on the right-hand side, we have the storage cost in terms of gigabytes for each method. So first, we have the fine-tuned checkpoints, the single task models, indicated in the black dashed line. So they have always 100% of normalized accuracy by definition. However, if you look at on the figure on the right-hand side, their performance, their storage cost grows linearly with the number of tasks, and they grow very fast. On the other hand, for our compression scheme, which is indicated by this dark blue line with Tomask plus task arithmetic, first it preserves almost always 100% of normalized accuracy, even with a very large number of tasks. For example, even with 20 tasks, we're almost preserving all the performance achieved by the single task models. On the other hand, in terms of its storage cost, although its storage cost also grows linearly with number of tasks, it grows like 32 times slower than the saving the fine-tuned checkpoints, and visually it's almost negligible. Apart from this, we also have like the performance of the 2 baseline model merging methods. The first one is task arithmetic, indicated by the green curve, and also the task merging, which was current state-of-art merging method in terms of this domain. We see that although they have a very nice performance with a small number of tasks, their performance degrades very fast with increasing number of tasks. And eventually, for example, if we have 20 tasks in total, their performance is almost reset to the performance of the zero-shot model, which is indicated by the gray curve. So this is the first application of Tomask. In the next slide, we're going to talk about the second application of Tomask, which is to improve model merging. So what we already have here is that we have constructed a binary mask for each task. And this actually allows us to have one more information if we examine the distribution of these masks. Like here, we know for each parameter, how many tasks are actually using this parameter. Or in other words, how many tasks are these parameters are being active for. And then that allows us to examine the importance for each parameter in the multitask vector. So on the right-hand side, what we plot here is what we call the mask agreement profile. Like we define this as the proportion of the weights being active for 0 task, 1 task, or also like or 8 tasks in total. For example, we have first a subset of weights which we term as catastrophic weights. These are the weights which are active for non-task at all after merging. So this is probably because their magnitude gets somehow destroyed after merging. And as a result, none of the Tomasks are selecting them for that task. They are completely useless after merging. And similarly, we also have a subset of parameters, which we term as selfish weights. These are the subset of weights which are active for only 1 task. And apart from those, we also find that there are some subset of weights which we term as universal weights, which are the weights active for all the tasks. So as we can imagine, these weights are the most important for the multitask performance. So based on this plot, we could identify the importance of each weight. And so the question we have is that we have found that the weights that are active for at most 1 task. And we already know from previous results that they would create task interference for all other tasks, which means that they might benefit 1 task, but they degrade the performance on all other 7 tasks. So are they still useful for our model merging performance? And we will show the results like after removing this set of parameters. And that's the result of our second application, which we term as consensus merging. So here we add to the plot a new curve, which is shown in orange, the consensus task arithmetic, which is a simple modification to task arithmetic that we remove the catastrophic weights and also the selfish weights after the model merging, after the aggregation. As we can see from this plot, in most of the cases, consensus task arithmetic outperforms not only task arithmetic, but also task merging, which is more state of the art than task arithmetic, especially if we have a large number of tasks, like if we have 20 tasks. Removing the selfish and catastrophic weights benefits more and more with larger number of tasks. So we have introduced these 2 applications. For the remaining slides, we're going to have more detailed overall results of applying our methods. First, we are going to present the performance of our methods on computer vision. So in this slide, we present the performance with the 2 different model sizes, the small VIT base and also the large VIT large. And we present the results across 3 different benchmarks, the 8 task benchmark, the 14th task benchmark, and also the 20 task benchmark. And we compare the performance of our methods with baseline methods, both in model merging and also in compression. And one remark here is that the numbers in the parentheses are the normalized accuracies, the average normalized accuracies, normalized based on the single task models. So the best we can do here is 100%. So we are first going to look at the performance of our compression scheme, which is shown in the last 2 rows. As we can see here is that across the different test scenarios with the small to large number of tasks and also the small to large model sizes, we are always preserving almost 100% of the performance achieved by the single task models, which again demonstrates the efficiency of our method in terms of model compression. And apart from that, we also have this highlighted zone of our performance of our consensus merging algorithms. Our consensus merging algorithm consistently improves over the baseline methods, especially if we have a large number of tasks. For example, if we have 20 tasks in total with the large variety, the largest variety large, we actually improve task arithmetic by about 5%. And one interesting thing here is that if we apply our compression algorithm using the small variety base with 20 tasks, we actually achieve an absolute accuracy of over 90% with 8.2 gigabytes. However, if we apply the baseline model merging algorithms, we spend like 11 gigabytes of storage cost, but only get an absolute accuracy of less than 80%. So we're actually able to get better performance with less storage cost. This results demonstrates again, like we have a very nice trade-off in terms of performance versus storage cost. So in these slides, we present the same results, but natural language domain. So here we test with the T5 large model across 3 different test benchmarks, the 7 task benchmark, and also we have a 8 question answering benchmark, and also we have their union benchmark, which has 11 tasks in total. First, we're going to have a look at the performance of our consensus merging. For example, if we examine based on the 8 question answering benchmark, our consensus task arithmetic algorithm improves task arithmetic by about 5%, while our consensus task merging algorithm improves the baseline task merging algorithm by about 6%. And we also have significant improvements when we test on the 11 task benchmark as well. In terms of compression, as we can see here, across these benchmarks, we are always able to preserve over 95% of the performance achieved by the single task models. In this slide, we are going to have a closer look at the task level performance across methods. So here, what we plot here is we plot for 3 different benchmarks where we have different number of tasks, the performance of each of these methods on each dataset individually. So here, first, we are going to have the performance of the single task fine-tuned models, which is shown in the black line. And that is the best we could do because they are the kind of the upper bounds after fine-tuning. And we also have this blue line, which is the performance of applying the Thomas algorithm to task arithmetic. As we can see, in all of these 3 data plots, the blue curve is almost always overlapping with this black curve, which means that in almost all the tasks and also across different number of tasks in total, we're able to preserve almost the full performance of this fine-tuned accuracy. Apart from that, we also have the performance of our consensus task arithmetic, where in most of the cases, it outperforms the 2 baseline methods, the green one by task arithmetic and also the purple one by task merging. Especially if we have a large number of tasks like the 20 task benchmark on the right-hand side, we can see that the orange curve is almost always fully surrounding the green and the purple curve, which are the accuracies achieved by task arithmetic and task merging as baseline methods. So finally, we are going to present ablation results where we slightly tune the weight pruning threshold. So recall that for consensus merging, we improve the performance of the baseline model merging methods by removing the weights used by at most 1 task. So the question is, what if we change this threshold by removing less or more weights? And we present the results about changing this weight pruning threshold on the right-hand side of this figure. So first, for consensus task arithmetic, we observe that we have performance improvements by removing, for example, only the catastrophic weights, the weights used by non-task at all. And we have the best improvements when we when we remove both the catastrophic and the selfish weights, where we set this weight pruning threshold to 2. However, for consensus ties, we have the best improvement when we just remove the catastrophic weights, which means that we only remove the weights used by non-task at all. So this result kind of shows that the best threshold is dependent on the model merging algorithm we use to generate this multitask vector. And we have a similar observation if we evaluate benchmark where we have 20 tasks in total. For consensus task arithmetic, we have a kind of optimal performance if we keep increasing this with improving threshold to 5 in total. And for consensus ties, the best improvement we get is to remove only the weights which are used by non-task at all after merging. So this is the result for the ablation studies on the weight pruning threshold for consensus merging. And those are almost everything we have for the presentation. Thanks a lot for your time. Please let us know if you have any questions. Thank you.